Adler, the co-founder and chief research officer of Celestia, to talk about the path to Gigabyte blocks. Take it away, John.
Hi, everyone. Good afternoon. I'm here to talk about the first, not the end step of Gigabyte blocks, but rather the first few steps of the journey of scaling Ethereum, specifically with data availability. Okay, so a bit about me. My name's John. I'm one of the co-founders of Celestia. I do protocol research and design at Celestia Labs, and do my best to lead the engineering efforts of the protocol team. Occasionally, I also shitpost on Twitter. Okay. So when it comes to scaling Ethereum with data availability, the talk of the past many years has been rollups, right? How does a rollup work? To make sure we're on the same page, it's a mechanism by which you can separate execution from data availability and ordering. So you could have one of several or several simultaneously different execution layers. For instance, here we have Arbitrum, Optimism, Base, Starknet, and of course there are many others. ZK Sync, Manta, I can't even name them all. But you can go on L2 Beat. There's like almost 50 at this point, layer 2s, rollups. And then there's another, in the upcoming tab, they have like another 30, 35 or something like that. And this is only the beginning. So why are rollups useful? Well, if we start with the premise that execution is the bottleneck, which is a generally agreed upon premise, then of course if you make the base trust layer, which in this case, in this example is the Ethereum protocol, if you make the base trust layer not do that execution, then it can do other stuff with those resources. So in the model that's kind of evolved for classical rollups, which have basically been what people have seen for the past couple of years, modulo the past few months, has been one where Ethereum, the layer 1 Ethereum chain, serves as a consensus layer that is responsible both for data availability and also settlement. But also, more importantly, it also has its own execution. So this is the unfortunate side effect that if a rollup wants to leverage Ethereum for data availability, it has to compete with other applications that are not rollups, but rather they're applications proper for some single shared resource, the gas. And this is not great because DeFi primitives and stuff like that can be not very expensive, but rather they can have a lot of financial value. And like the ability to take a global lock on the entire shared state of Ethereum to process your financial transaction in any world where there's a large amount of finance going on the space layer, that is going to be expensive. So how do we get around this issue and make data availability a separate thing? Now we're going towards a modular blockchain stack. And this is what people have been kind of building towards for the last few years. Rollups have been deployed to separate out execution. And now we have data layers and other DA mechanisms being deployed to further modularize the stack and allow Ethereum to be used more for settlement and not for data availability. So you have protocols like Celestia, and you also have mechanisms rather than entire protocols like EIP 4844 that essentially only do data availability and do not also do execution. And what this means is if your execution layer wants to leverage one of these data availability layers, it doesn't have to compete with, say, some DeFi applications. It only has to compete with other rollups, and it only has to compete for data availability, not execution. Moreover, these data availability mechanisms have the nice benefit that they can be substantially more scalable than a layer 1 blockchain, like a base trust layer that also has other responsibilities, which means that the data availability throughput of these data layers can be substantially larger, as we'll see in a few slides. Spoilers. Okay, so what else have we seen come out from these modular blockchains? This is an example of a screenshot from a rollup as a service or RAS provider called Conduit, literally just from, I think, less than 2 weeks ago, on February 21st. They released their product here. It essentially allows you to spin up a rollup as easily as you deploy an application, a smart contract, where you can basically choose, and you can see the 3 layers here. You can choose your execution layer, your execution stack, which in this case, they're both EVM stacks, the OP stack and Arbitrum Orbit. You can choose your settlement layer, exactly like in the previous picture, where you can settle on Ethereum L1, or you can also settle on some L2s. And you can choose your data availability layer. So this actually allows you to deploy not just L2 rollups, but also L3 rollups. So for example, an execution layer built on the OP stack on top of the base L2. And these are the kinds of things that we're seeing emerging now that we have scalable data layers and that DA is no longer the bottleneck for a rollup's cost. Which of course, I'm not going to talk about the issue of if DA is not the cost, then execution might become the bottleneck yet again for these rollups. That's for other people to solve. Here we're going to talk just about the data availability part of this. Okay, so if you were to build something like this that settles on, let's say, Ethereum and that uses Celestia for data availability, how would you go about actually doing that in practice? So this is where this application called Blobstream comes in. It was formerly known as Quantum Gravity Bridge, which is a terrible name, which is why it's now called Blobstream. And it's not a bridge in the traditional sense of a token bridge that is bidirectional, that allows you to move assets and or messages between 2 chains, or 2 domains, as James Presswich would say. Rather, it's a unidirectional relay of information from Celestia to an EVM chain. It could be Ethereum, it could be Base, it could be Arbitrum, for example. Any EVM equivalent or EVM mostly compatible chain would be able to basically use Blobstream out of the box. That being said, there is also the nice property that any execution layer, for example, Solana, which has a completely different execution model than the EVM, could also use Blobstream without any changes to the Celestia protocol. And we'll get into why in a bit as I explain how it works in detail. But the initial implementation is just for EVM chains. Okay, so how does it work? I'm going to try and go into a bit of detail to satisfy some people because in some previous talks I've given about Quantum Gravity Bridge and Blobstream. I kind of gave a high-level overview. Now I'm going to go into a bit more detail since this is a hacker conference, after all. So you can see kind of some details of how it works and some of the nuances around the security assumptions. So how does this work? The Celestia chain is a Comet BFT chain, like a Tendermint chain, that has a validator set. The validator set signs over every block to give it finality. In some regards, this is similar to the Ethereum consensus protocol, where blocks are final after they receive votes from a cumulative at least 2/3 of the stakers or voting power of the chain at a particular height. Okay, so if you want to know that some data is available on Celestia on your EVM chain, which will use Ethereum in this example, how would you do it? Well, like many bridges, you need to run a light client of the Celestia chain in the EVM. And how do you run a light client? You have a smart contract that verifies signatures and keeps track of voting power so that whenever it is relayed a new header, it checks to see, does the header actually have enough consensus on it? Okay. I mean, this is like fairly standard light client stuff. At this point, nothing special is happening. But what guarantees does this provide? The nice thing about this mechanism versus, for instance, a data availability committee is that if a majority of Celestia validators are dishonest, then sure, they can trick the bridge or the relay, but they are dishonest in a way that is accountable because they have to make signatures. They have to make digital signatures, which can't be forged. Since it's accountable, it means that they can be slashed. The data availability committees don't have this property, right? And the data availability committee is purely up to the reputation. Okay. Now, some security nuances. One thing that was very important to us when we were kind of implementing and designing Blobstream as a whole stack is to make sure that it's secure and that it has the slashing property, which a lot of other data availability solutions for Ethereum do not have, right? And if you want to know, if something is secure, the first thing you should ask is, how do you do slashing? Because basically every DA solution that claims to scale Ethereum, unless it's part of the Ethereum protocol itself, is going to have some sort of economic stake, some sort of slashing, etc. If it's not part of the Ethereum protocol itself, such as EIP 4804. Okay, so how do we do slashing? Or rather, what nuance do we have here with slashing? There's kind of, there's this issue that what happens if someone, or in this case, the Celestia validators, rather, don't sign? If they don't sign, then you can't slash them because slashing only works if you have digital signatures from at least a large number of validators to show that they voted for, let's say, an invalid block or a block that is different than the one on the canonical Celestia chain. So what happens if they just stop voting and they just freeze the bridge? Then you can't slash them because you don't know that they've stopped voting. And the reason you don't know they stopped voting is because, like many Tendermint chains, Celestia uses ETHDSA instead of ECDSA. And on Ethereum, you can't really validate 30, 40, 100 ETHDSA signatures in a single transaction. That would cost, like, I don't know, a billion gas. So that's not going to happen. So what's the solution to this? The solution is that this is how it used to work. I'll go into improvements in the next slide. So how would it work? The Celestia validators would post their signatures into Celestia blocks to make them available. After all, Celestia is a data availability layer. Right? So kind of self-referentially, they would post their signatures, their ECDSA signatures, because they have two keys, one ETHDSA and one ECDSA key pair. They would post their ECDSA signatures to Celestia itself. And this allowed them to be slashed if they stopped signing. So then you get slashing both for equivocation or invalidity, and also slashing for liveness failures. And both of those conditions are very important to have. Again, if any protocol claims to scale Ethereum, the first thing, unless it's part of the Ethereum protocol, the first thing you should ask is, how do you do slashing for both liveness and safety failures? Okay, so now the issue about what I just described, where you have to post signatures into Celestia and where you have two different types of keys, one ETHDSA and one ECDSA, is kind of cumbersome. It's kind of a bitch. So how do we solve it? Oh, I'll go back to the previous slide in a sec. How do we solve it? This is where Blobstream X comes in. So this is an improvement to Blobstream that uses none other than zero knowledge proofs, the thing that everyone has been hyped about for years. And you actually verify ETHDSA signatures inside the ZKP so that they don't have to be verified in the EVM directly. Essentially, you're running a ZK Lite client of Celestia in this case. What benefits does it have? Now, Celestia validators don't need two key pairs, one ETHDSA and one ECDSA. They only need their single ETHDSA key pair. And more importantly, you don't have to do this whole thing where they make their ECDSA signatures available because they don't need them in the first place. They only have a single key pair. That key pair is used to vote on Celestia blocks proper. If they stop voting on Celestia blocks, they'll get kicked out of the validator set, or they'll get slashed by Celestia social consensus, regardless. So this kind of solves all that issue and makes everything substantially easier. Okay. Now, let's say you're a developer and you want to use Blobstream. Now, we've talked a lot about kind of how it's implemented and stuff, but how would you actually use it if you're a developer? Be it a roll-up developer, maybe you're some infrastructure developer, maybe you're an application developer and you just want to skip over all the infrastructure stuff and just go straight to having an application that uses some off-chain data availability solution. It's actually quite simple. Literally, the entire interface for using Blobstream and Blobstream X, because they have identical external interfaces, is this one function. This one function allows you to verify is some data in a Celestia block, and has the Celestia block been previously relayed by the Blobstream contract. And the implementation of this function on both versions of Blobstream essentially checks all the necessary preconditions and then returns you true if in fact that data is available. So it's very simple. There's only a single function that needs to be used to to verify this. Okay, so what do we get out of all this in practical terms? Right? I've talked to you about Blobstream existing, sure, but what do you get out of it? So on the left here, we see the average throughput of the Ethereum chain and the average availability of call data on the Ethereum chain, which is in the order of like 10 to 15 kilobytes per second, which is also on the order of dial-up internet, right? Which I think was like 56 kilobits. It's on that order, which is not great. Celestia, which currently on mainnet supports 8 megabyte blocks every 12 seconds, has a throughput that's closer to 700 kilobytes per second. And the difference in orders of magnitude, as you can see here. And there's also the difference in order of magnitude between dial-up internet and broadband internet. So this is really crypto's broadband moment, where you finally have access to an abundance of trusted data availability, and you can build applications that straight up would not have been possible to build without this abundance. Right? Like internet streaming, YouTube and stuff, probably wouldn't work very well if everyone only had dial-up internet. And now we finally are getting into the broadband stage, and that's not where things end, right? This is only the beginning. It's only the beginning of the path towards the end when we're going to gigabyte blocks. And this is how, years in the future when we have throughputs on the order of 100 megabytes per second, not just on Celestia, but I'm sure in other data availability solutions as well, all scaling Ethereum, the throughput that was available to us in years past, that available, well, not today, but let's say 4 months ago, prior to the launch of Celestia, it's going to look like those tiny little blips on the left, and we'll be wondering, how did we ever do something with, basically dial-up internet? Okay, what does throughput give? Among other things, it'll give a reduction in fees. So this one here is taken from L2 fees today, where you can see that even on layer 2s, because of the very high cost of call data and data availability, things like swapping a token can easily take $1. And Ethereum hasn't even hit mainstream adoption yet, right? I mean, maybe some will argue that it's mainstream already, but I think a lot of people will say we are still early, and that's my opinion as well. And we're looking at fees that are already $1. Imagine how expensive they will be in the future. But if you use scalable data availability solutions, then 99+% of this fee essentially goes away. And here's a concrete example from Manta Network, which integrated Celestia underneath back in December. So this was literally just like 2 months ago. And in those 2 months, they've saved almost $2 million in fees that they would have had to pay for data availability had they not used Celestia. Okay, so kind of closing remarks here. We're finally entering an age where you can access abundance, and with that abundance, you can build whatever with Celestia underneath. And to that end, we're also going to be hosting a modular hackathon later this month called the Infinite Space Bazaar. So keep your eyes peeled for that if you want to participate. It's an online hackathon. And if you want to find out more, here's our website and our GitHub. We build basically everything in the open. No closed repos. Everything's in the open. Everything's completely free and open source. And here's also Twitter if you want to follow us for socials. And with a few minutes left, I'm opening the floor for questions. Okay, I see one hand for questions over there. Do we have a mic for questions? Okay, I don't see a mic, but if you yell it, I'll repeat the question. Okay, so the question is around, has there been any thinking or research into using KZG commitments or other polynomial commitment schemes as a replacement to fraud proofs? So currently, Celestia is built around, I don't want to say built around fraud proofs, but rather it currently supports bad encoding fraud proofs, which means that if its block is incorrectly encoded and constructed, there is a fraud proof for that can be distributed to the network to show that it's incorrect. But like any fraud proof scheme, you can always have some sort of validity proof, or even better, you can have some polynomial commitment that is like less expensive than a ZK proof, but that serves the same purpose for this specific task. We haven't done much research ourselves on the topic, but I know that the Ethereum community and also the Avail team have been researching that, and my understanding is that it is totally possible to do. I think Avail implemented KZG commitments and also data availability sampling on top of that. So that is something that we would expect the Celestia protocol to support in the future. And we would also expect to support it in a way that doesn't necessarily break backwards compatibility with the current commitment scheme. So you get the benefits, you're going to be able to get the benefits of not needing fraud proofs, but you shouldn't have to worry about any backwards compatibility breakage. Okay, thumbs up. Cool, with that, I'm out of time, so, quick question. Will we support Bitcoin L2s? Well, I can't say will or won't, but I will say that there have been discussions and I think some concrete efforts towards this Blobstream technique being usable on Bitcoin through techniques like BitVM. So maybe in the future, yes.